We expansion.
right? So
Minus zero. Minus
right, so this we define the Mobius function. So mu of n, so it is -1 to the power k, where k is the number of prime factors in the prime factorization, and if all of them are distinct, that is only one, then I have this, otherwise it is 0, right? So next we define, so this is the arithmetic functions, right? So next we define one more function called the Euler's Totient function. So this is phi of n. So the definition. So for n greater than equals to 1, so if n is greater than equals to 1, the Euler Totient function, so this phi of n is defined to be the number of positive integers not exceeding n, which are relatively prime to n. Right. So then what will happen is, so this is fine. So this is nothing but, so phi of n, it is summation over all k equals to 1 to n, such that k and n is GCD is 1. So this is relatively prime, and this is summation is over 1. So it counts the number of relatively prime things, right? So let us see for small values what is the phi of n. So this is n is here and phi of n is here. So suppose n is 1, then phi of n is 1, right? It's fine. So if n is 2, then what happens? What is phi of n?
I want to see the definition again.
Yes.
The the number of positive integer not exceeding n relatively prior to n.
Relatively prime. Yes.
Summary k kn kn this is kn is to 1.
Right.
Okay, so it's the 1.
Right.
That's the 1 only. K equal to 1, n
Right.
equal to 2, so k is equal to 1 and 2. And we have 2. Is right.
So for 2, how many? What will be the thing? Phi of n?
2. Yeah.
No, it is 1, right?
Huh? We have
Because
1 and 2. K equal to 1 and k
yes,
equal to 2.
if k is 2, then it is 2, right? GCD of 2 comma 2 is 2, right? It is not
Okay. Yeah.
right. What about 3?
3, we have 2.
Right. Then 4.
4 equal to 1 and 1 and 3.
Right. So
Yeah.
2. 5.
1, 2, 3, 4.
Right.
Yeah.
6.
61, and not 2, not 3, not 4, 5.
Right.
Yes. Yeah.
So similarly, 7 you can check 6 of all the 6 previous 6 will work.
Mm,
8 you can check 4 of them will work, like this. For
mm.
9, tell me what will be 5 of 9?
1, 2, 4,
Right.
5,
Hmm.
7, 8. Yeah.
Right. 6. And similarly, you can check for 10 it is 4. Right.
Uh,
Right. So this is the, so for some small values of n, we get the part is 5 of n. Right.
okay. So the maximum of 5 would be 6
Maximum
of 5n.
no. It will go, because you can see will come to maximum. It can be anything. So because every prime number, all the numbers before that will work, right? So this number is increasing.
Mm, mm, mm.
Okay. So there is a relation between the next theorem states that.
Okay, okay. Because the prime number is infinity.
Yes, yes.
So if we check the infinity n, that would be infinity 5.
Right, right. So all the numbers, so prime numbers are infinite. So prime number can be large. So for
Mm,
large prime numbers, the number of phi n will also be large, right?
mm, mm, mm.
Yes.
Yeah, that's right.
So if n is greater than 1, then we have a nice relation that summation over all the divisors of n, d divides n. The phi of d, that is nothing but the sum is actually equal to n. Okay. So yes, the statement is clear, right?
Yeah, yeah.
Right. So let us see the proof. So let us denote the set 1, 2 up to n. Then we distribute the integers of s into as disjoint sets. So the set we take all the integers up to n. Next we distribute the integers of s into disjoint sets as follows. Okay. For each divisor of n, d of n, let a of d denote all the integers k such that the GCD of k and n is actually equals to d, where k varies from 1 to n. So this is the set, right?
Mm,
So we are actually taking all the integers such that the GCD of k and k and n is actually exactly equals to d, right?
mm. For it divided.
Right. So d is a divisor of n. So that is AD contains those elements of S which have the GCD d with n, right?
Mm,
So okay. So now you can see that this AD they form a disjoint collection, right? So these sets AD. So these are disjoint, right? So they cannot have same element in common, right? Because this n is fixed. So their GCD cannot be both d1 and d2 for different d1 and d2, right?
mm, mm, mm.
So these sets AD are disjoint, forms a disjoint collection whose union is S. Right. Now, uh, so if f of d, So this denotes the number of integers in AD. So this is the cardinality. So this denotes the number of integers in AD. So if I take that, then if I take the summation over all the f of d's, that is d divides n,
Mm.
f of d. So that is nothing but equals to n, right? Because uh, total AD, that union contain all the elements of S, and S has n elements from 1 to up to n, right? Fine.
I read. I read
Yes.
from begin. Yeah.
Yes.
Mm. One to n.
Right.
Integer update into the choices that follow. Choice divisor d of n
Right.
into d of n. K.
Hmm.
So that k n equal to d. K. For example, n equal to 6. Right, n equal to 6. So the would be 1,
Yes.
2,
1, 2, 3.
6,
Right.
and k will be uh, usually of 1, 6 equal to
Yes.
1.
Okay. Let me write down. Yes. So
Okay.
for suppose we take n equals to 6.
Yeah,
So n equals to 6. Then the divisors. So d is equals to either 1, 2, 3, and 6. Right.
yeah.
So then a of d.
I have d
So this is only 1, right?
1,
Because a of d is the set of elements such that the GCD of 1 and 6
2 and 6.
means the k and 6 is 1, right? So that is only so this will be there, and 5 will also be there. 5 will be there.
5 today.
Yes, because these are all the elements such that k comma n GCD is d. So d is 1 here, right?
The they should be 1, should be 2, should be 3, should be
Yes, yes. So here we are calculating a of 1 first,
I want. Okay, okay.
right?
Uh, y is fine.
Yes, because the GCD is 1, right? With 5, 5 comma 6, the GCD is 1, right?
Yeah, yeah. Equal to d. Equal to d.
Right. So similarly, if I calculate a of 2, so then I have 2 is there and 4 is there.
2.
Uh, so this one is, if I take 3, so only 3 is there. And if I take 6, and then only 6 is there. So these are a this form a disjoint collection of all the elements up to 1 to 6.
1, 2, 3, 4, 5, 6.
Right.
Oh, but how we ensure that will be destroyed?
Yes, this is disjoint because that is what I told, right? So if suppose two elements, suppose d1 and d2, so they have one element in common, right? But that is not possible, right? Because a same integer k cannot have GCD both d1 and d2, right? For two different integers.
Why? We have different d,
Right, we have different d.
different d, the same n.
Yes, same n and same k. That
Uh,
is not possible, right?
so it's not possible. It's same k.
Right.
If k same and d n same, k
Yes.
different, n same, so d is different.
Yes.
Why? GCD. Yeah, yeah. But
right?
that's okay. But how we ensure that we fulfill from 1 to n?
Yes, yes. So the thing is, so suppose some element is not there, right? So some element is missing, right?
Is it
So
possible or not?
yes,
Is it possible if something missing here?
yes, yes. That is not possible. That is I'm saying that suppose some element is missing, right? So then what does it mean? So it means that if I take suppose if I take that element k along with n, right? So then it has the GCD some element that is not dividing n, but that is not possible, right?
Wait, I think a little. Hmm? If missing K1 is missing.
Yes, suppose k1 is missing, right? But the thing is, what I have is k1 along with n. So this will be some GCD will be right. So it is some this GCD is d1, right?
K1, D1,
Right.
B1 maybe one or something is right.
Yes. Suppose the GCD is d1, right? But d1 divides n, right? Since it is the GCD. So this k1 must have come into this set A of d1, right? Because we are taking all the collection of divisors of n, right? So d1 is a divisor of n. So we cannot miss any element, right?
K1 equal to D1. Oh, wait, I think, for example, we are missing the number 5.
Right.
Number 5. And
Uh,
the 5, 6 equal to 1.
yes, but that must come into this set of A of one because one is a divisor, right?
Ah, mm, yeah, yeah, yeah,
Right.
yeah, yeah. Mm,
So this part up to this part is clear, right?
mm, it's okay. Mm. Contain eliminate.
So what we saw that the sets AD, so this forms a disjoint collection, and their union is the whole set S, right?
The set ID form addition collection. Yeah, 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 yeah. This one. If
Right.
FT is not the number integer in ID, symbol A1 equal to 2.
Hmm.
So F1 equal to 2 is right.
Okay.
Just
Yes, yes. F of one. Yes. In this case, it is the number of elements. So f of one is two, right?
mm, F of 3 equal to 1.
F of 3 is 1, yes. So
Yeah.
their sum is actually equal to n because that is the union is whole set S, right? So all the elements of S are in a sum of A of D, right?
Uh, yeah, yeah. This is okay. Yeah, yeah.
Right. So up to this is fine. Next, what you have is so but suppose K and N. So this has GCD is D. So this is if and only if I divide by D, their GCD is one, right?
Mm,
Right. And uh, K is strictly less than N or less than equals to N if and only if this lies between k comma k divided by d that is less than equals to n divided by d, right?
mm, yeah, yeah.
So therefore if we let q to be the integer k divided by d so that I can take, so there is a one to one correspondence between elements of AD and those integers Q that satisfy this relation, that Q is less than equals to n by d, where Q and n by d. So this has GCD is 1, right?
35. That satisfy is okay.
Right.
But, 1 to 1
1-to-1 correspondence.
corresponding. That means for 180 we have one integer Q.
Right.
That's okay.
Right. But what is this Q? So Q is the number of this is phi of n by d, right? That is the number of things that is co-prime, right? They are relatively prime to n by d. So what is Q? Q is nothing but phi of n by d. So number of elements that are co-prime to this number n by d.
Huh? Q equal to the number of n.
So this Q with n by d is 1, right?
Uh,
And so how many Qs are there? So the number of Q is nothing but uh, number of such Q, not the so so number of Q such that your GCD is 1. So that is what? That is nothing but phi of n by d, right? By definition.
5.
That is this Euler's function that we define. The number of
I want to check the 5.
yes, yes. So yes, this is the right.
Ah, n equal to 1. N equal to 1. Yeah. And
So this is the number of positive integers that is relatively prime to n, right?
uh,
So that is what here we are doing, right? So this Q comma n by d, that is 1. Then the number of such Qs is nothing but phi of n by d.
but uh, Q and it's E1 not one. We have one Q only.
No, no. The thing is, yes, that is so. For example, Q is k by d, right?
Mm,
And we have a one-to-one correspondence between AD and those integers Q, such that this happens.
mm, and by D.
Okay, let us see through the example. That will be easier.
Mm,
So, for example, let us take this d equals to 2. Let us take this case, right? So, for this example, suppose d is equals to 2, right?
mm,
So, then what I have, and k, let us take k equals to 4, right? Then I know that k comma is 4 comma 6, the GCD is 2, right? Now, if I divide by 2, that is 2 comma 3, that is 1, that is fine, right?
mm,
So, what is q here? So, q is k by d. So, it is 2 here, right?
mm.
So, how many integers are there such that, so for example, q is 2 and n by d is also so n by d is n is 6 here and d is 2, so n by d is 3. So this is q comma n by d. So q comma n by d, how many q's are there that is less than equals to n by d, such that your GCD is 1. So it will work for 1 and 2 because n by d is 3. Right. So there are two integers. So that is nothing but phi of 3. Phi of 3 is 2. Right. So there are two integers such that the GCD with n by d is 1. So the cardinality of A2, so this A2 is matching with what is phi of n by d. So that's why we say that there is a 1-to-1 correspondence.
Mm. Mm. Two. Yeah. Actually, from Q,
Yes.
usually of Q and divide D equal to 1, I got is, but the conclusion, the
Hmm.
number set QE5 and divide D. So it's the summation of on divisor of
Right.
n power d such that k usually of k n over d equal to 1. Q 1-to-1 corresponding between element ID. Element of ID here is number elements of IDs, right?
Right.
Uh, and the Q dash certify.
So the number of elements of AD has a so that is equal to phi of n by d. So that is what we are proving.
Hmm. What do we want to rule here is number of
Yes. So from here the conclusion is so from here this implies that f of d, that is nothing but this phi of n by d. So that is what you want to show.
mm, mm,
Right.
mm. Yeah.
So now you already have seen that the summation over all d, f of d is n. So we can just substitute that. So hence summation of d divides n, f of d, that is nothing but d divides n, phi of n by d.
Mm,
So that is n, right?
mm,
But the thing is, the summation is running over all the divisors of n, right? So n by d, so that is also a divisor of n, right?
mm,
So I can just change the notation. From here I can directly say, so phi of d, that is n.
mm,
So this is what we wanted to show,
yeah.
right? So this is fine, right? Up to this one.
Yeah, it's okay. Mm,
Right. So this, what does it say? It says that if I take the summation of phi of d over all divisors, then it's equal to n.
mm,
Okay. So the next theorem is the relation between these two things, the mu function, the Mobius mu function, and this Euler's Totient function.
mm,
Between phi and mu. Okay. So there's the theorem. So if n is greater than equals to 1, then we have this phi of n is nothing but d divides n mu of d times n by d.
Mm. Yeah, yeah.
Right?
Mm. Mu of t. Mm. Mm. Multiply with n for d on
Right.
divisor. Yeah. Mm.
Okay.
Yeah, yeah.
So let's see the proof.
We can do it in the next session. I have
Okay.
our ugly to office. Yeah,
Okay. Okay. So we'll do in the next one.
yeah. Thank you.